So, we will take up a couple of examples to illustrate this application of linearized theory, and the first problem that we will take up is two dimensional flow past a wave shaped wall, a very well known classical problem, also popularly known as Eckert's problem. Now, let us consider flow over a wave shaped wall. We will now denote these two direction x 1 and x 2 by x and y. So, instead of using x 1 and x 2, we will now use x and y, and let us say that this is the and we consider one wavelength of the body L, and this amplitude is given by h. So, the wall is given by y equal to h sin alpha x, where so h is the amplitude and alpha is the wave number. Amplitude, which are the maximum from y equal to 0, and alpha is the equivalent to wave number equal to 2 pi by L, or L is wavelength. We will consider the flow is coming from left to right with undisturbed stream of m infinity. Now, for subsonic or supersonic flow, we have 1 minus m infinity square d 2 phi dx square plus d 2 phi dy square equal to 0. And these are phi is perturbation potential, these are subjected to boundary conditions. at infinity what we know about the perturbation are that they must be finite, d phi nothing more than that, d phi dx and d phi dy must be finite. And on the wall the slope of the wall, that is dy dx on the wall is the slope of the streamline on the wall, which can be linearized for very thin geometry dy dx on the wall is where we have made this assumption that since the body is very thin, the velocity components on the wall is same as the velocity components at y equal to 0. For the body, very thin body, this approximation is first order accurate and consistent to our first order perturbation theory. And then we have made further assumption that, which of course again consistent with the small perturbation theory, that u is much smaller compared to u infinity and hence their sum is close to infinity. So, here there are two assumptions involved. One, that v component of v and u component of velocity on the body is same or very close to the velocity that would have been at y equal to 0, and then sum of u infinity and perturbation along x is very close to u infinity itself. Both these assumptions are consistent with first order perturbation theory and is acceptable. Now, to complete the solution of this problem at hand, that is flow over a wave shaped wall, we need to solve this equation subjected to these boundary conditions. Now, first of all, before solving the equation, we should see that the equation changes its nature as m infinity changes from less than 1 to more than 1. When you see that when m infinity is less than 1, both the term are of same sign. However, when m infinity is more than 1, the two terms are opposite sign, and this essentially changes the nature of the partial differential equation that we have here. When both the terms are positive, this equation is of elliptic nature, while when the two terms are of opposite sign, the equation become hyperbolic. As now, if we may call back that when the equation is elliptic, to solve a partial differential equation, we need to satisfy boundary condition at all boundaries. However, for solving the hyperbolic partial differential equation, we do not need to satisfy boundary condition in all direction. Only the initial conditions are sufficient. Also, the hyperbolic equation supports discontinuous or solution, while the elliptic equation supports only continuous or smooth solution. So, we see that the equation changes its nature. In case of a subsonic flow, the equation is elliptic. When the flow is supersonic, the equation becomes hyperbolic. So, we need to solve these this equation separately for subsonic or supersonic flow. So, the first case we will consider a subsonic flow. So, let us consider a subsonic flow. We now have 1 minus m infinity square is greater than 0 and the equation is elliptic. That is, in this case the solution will be smooth over the entire flow domain or over the entire flow field, and we need to satisfy all the boundary conditions together to get the solution. And we let us say 1 minus m infinity square is beta square for convenience, and the equation can be written as d 2 phi dx square plus 1 by beta square d 2 phi dy square equal to 0. This equation can be solved by separation of variables. Which says that phi, which is a function of x y, the perturbation potential, can be separated into two functions each of one variable, say f x g y, and this when we substitute gives us f double dot by f plus 1 by beta square g double dot by g 0. Now, the first term is function of x and second term is function of y only. Now, sum of these two functions can be 0 for all cases only when both of them are constant. This is function of x, this is function of y, and sum of them is 0. That can happen only if both of them are constant. So, and let us set that constant as we are taking square, taking the constant as a square just for convenience. Now, this gives us a solution that f equal to a 1 sin k x plus a 2 cos k x and this gives g equal to b 1 e to the power minus beta k y plus b 2 e to the power beta k y. Now, the boundary conditions at infinity needs that the perturbation velocity components must remain in finite at infinity, that is at x equal to infinity as y equal to infinity. So, boundary condition at infinity imposes finite perturbation velocities at x equal to infinity and y equal to infinity. Now, x of course remain finite, f remain finite for all values of x, even at x equal to infinity this f remains finite, but looking to g we see that this goes on increasing with y. So, if this has to remain finite, then this b 2 must be 0. This implies b 2 equal to 0. Now, for the wall boundary condition, the wall boundary condition we have written as V x 0 equal to u infinity dy dx wall. Now, V x 0 which is d phi dy at y equal to 0. That is f x so V x 0 becomes minus a 1 sin k x plus a 2 cos k x into b 1 beta k e to the power minus beta k y, that equal to u infinity into dy dx, that makes u infinity h alpha cos alpha x. Now, this can be satisfied only if A 1 is 0, there is no sign term on the right hand side. So, there must be no sign term on the left hand side. So, A 1 must be 0, k must be alpha, and A 2 B 1 beta k minus is u infinity h alpha. So, can be satisfied if A 1 equal to 0, k equal to alpha, and minus A 2 B 1 beta k is u infinity h alpha. So, we can now substitute these values of, we have B 2 is 0, A 1 is 0, and we have got the product of A 2 B 1, and this and implies that phi x y, which is f x into g y, A 1 is 0. So, f 2 remains only A 2 cos k x into g y b 1 e to the power minus beta k y, and then we can substitute what they are. Minus u infinity h by beta e to the power minus alpha beta y cos alpha x. Or in terms of the wavelength, instead of wave number, this can also be written as minus u infinity by beta h e to the power minus 2 pi beta y by L into cos 2 pi x by L. The perturbation velocity components u is d phi dx, that becomes u infinity h alpha by beta e to the power minus alpha beta y sin alpha x, and v equal to d phi dy into u infinity h alpha e to the power minus alpha beta y cos alpha x. The total velocity field, of course, can be obtained by adding u infinity to the u component. The pressure coefficient is now looking to these properties, perturbation velocities u v and pressure coefficient C p, we can see that the perturbation decays with y. As y increases, perturbation velocity components decreases, so is the pressure coefficient. So, the largest perturbation occurs at the boundary. All these show that largest perturbation occurs on the boundary. And the pressure coefficient on the wall, that is pressure coefficient on the wall, is minus 2 alpha h by beta sin alpha x. We see that the pressure distribution on the wall is in phase with the wall. The wall is also given by h sin alpha x. Consequently, the pressure distribution is symmetric about the wavy wall. And this gives that there will be no drag force. There will be no drag force acting on this body. We also see that as Mach number increases, pressure increases. Actually, this increase in quantitative term is proportionally to 1 by beta. This beta is known as Prandtl load factor. Or Prandtl load parameter. Also, we see that the perturbation velocities and pressure has an attenuation, that is, as we go away from the wall, as y increases, the perturbation velocity and the pressure coefficient decreases. So, in the limit of y approaching infinity, the perturbation velocities become 0, which again is an standard boundary condition used in incompressible flow, where it says that the perturbation at infinity is 0. So, we see that we approach that situation subsonic flow. However, we also see that However, since the factor beta is present in the attenuating factor, so the attenuation decreases with Mach number. As m infinity increases, the attenuation decreases. So, that is when m infinity is larger within the framework of subsonic flow, then the attenuation will be felt at a much greater distance compared to a low subsonic flow. A high subsonic flow will be felt at a much greater distance compared to a low subsonic flow. Now, considering the pressure term, pressure coefficient, that C p is minus 2 h alpha by beta e to the power minus alpha beta y sin alpha x. We can see that the parameters involved here are 1, 2, 3, 4, 5, 6. There are 6 parameters involved: C p, h, alpha, beta, x and y. Now, these parameters can be arranged in this fashion, that C p beta by alpha h, the constant we can forget, is some function of alpha x and alpha beta y. So, where the left hand side is a modified pressure coefficient, and these are of course modified coordinates. So, you see that it is possible to express the pressure, a modified pressure, in the form of some modified coordinates. So, that instead of 6 parameters we now have 3 parameters. That means, it is possible to reduce 3 parameters, and what it implies that if we have 2 bodies with these coordinates being same, then this pressure coefficient will also be same, this modified pressure coefficient will also be same, and hence knowing the solution for one such body, we can obtain solution for similar other bodies. So, this is basically a similarity rule, in which a similarity rule which implies that there is some possible combination. When used, then the total number of parameters involved will decrease. So, in this case, of course, we are getting this from the known solution, not a priori. However, it shows that if we have this type of combination, that means instead of coordinates x and y, if we express the coordinates in the form alpha x and alpha beta y, then and the pressure in the form C p beta by alpha h, then for all walls for which alpha x and alpha beta y are same, they will have same modified pressure given by this relation. We can have some further insight or further assumption, further result from this solution. First of all, that our perturbation velocities are such that u by u infinity and v by u infinity are small. According to small perturbation theory, that is when the solution is valid, u by u infinity and v by u infinity are smaller than 1. Now, looking back to our u by u infinity and v by u infinity, the u by u infinity equal to h alpha by beta e to the power minus alpha beta y sin alpha x. This is much smaller than 1, or this is possible if alpha h by beta is much smaller than 1. The same thing we get from v by h, v by u infinity is h alpha e to the power minus alpha beta y cos alpha x much less than 1. So, this implies h alpha is much less than 1. Of course, if h alpha by beta now, if h alpha by beta is much less than 1, then of course, h alpha will be much less than 1. So, together imply that alpha h by beta is root over 1 minus m infinity square is much less than 1. So, if this is satisfied, only then the solution is applicable. So, what we see that for the solution to be valid, it is not essential that h itself has to be very small. It is required that the combination h alpha by root over 1 minus m infinity square, that must be very small. If this condition is satisfied, the solution is valid, or that the solution is within the framework of small perturbation theory. Also, we have used the linearized equation to solve this problem. Since the linearized equation is used, we have implicitly assumed that 1 minus m infinity square is much larger than the term on the right hand side, which is required when m infinity is very close to 1. That is, this term is much larger than this term. This is implicitly assumed. So, we have implicitly assumed this, or in this case this will become m infinity square into gamma plus 1. The largest possible value for u by u infinity is h alpha by beta, or what we have is m infinity square into gamma plus 1 alpha h by 1 minus m infinity square to the power 2 by 3 is much less than 1. So, we have implicitly assumed this. Now, what is the meaning of this? We have earlier stated that this term is negligible when m infinity is not close to 1. In particular, when m infinity is close to 1, only then this term become comparable to this one. So, this term cannot be neglected for m infinity close to 1 or for transionic flow. Now, what it says that this can be negligible if this is satisfied. So, if this is satisfied, then the flow is not transionic. So, if this is satisfied, so, we see that this particular parameter decides or sets whether the flow is transionic or not. So, we can call it a transionic parameter, and what we see that this transionic parameter includes gamma, that is the gas. So, just the value of free stream Mach number or even the geometry is not sufficient to decide whether the flow is transionic or not. Also, what the gas is that decides whether a particular flow is transionic or not. That means, flow at a same Mach number over same geometry may be transionic if the gas is a particular gas, but may not be transionic if it is other gas, depending on the value of gamma. Another important is that it contains the parameter power 2 by 3 by 2, and this is what is the condition for occurrence of local sonic velocity. Let us now consider the other component of free stream velocity, that is perturbation velocity v by u infinity as alpha h e to the power minus alpha beta y cos alpha x. On the wall, this term becomes on the wall we know y equal to h sin alpha x. So, minus alpha beta h sin alpha x into cos alpha x. This we can write alpha h cos alpha x, and this term e to the power minus alpha beta h sin alpha x we can expand in power series to get 1 minus alpha h beta sin alpha x plus higher order terms. Now, the maximum value of this second term is alpha h beta. So, maximum value of the second term is alpha h beta. Now, in our small perturbation theory, we have approximated that v by u infinity, this term v by u infinity wall is v by u infinity y equal to 0, that is only this much. The small perturbation theory assumed v by u infinity wall is v by u infinity y equal to 0, and in this case that equal to alpha h cos alpha x. Now, this to be now this is satisfied if alpha h beta is much less than 1. And in all these relations, alpha h can be replaced by, in all the relations, alpha h can be replaced by local inclination theta. And this then all these conditions then can be written as hence small perturbation is applicable if theta by root over 1 minus m infinity square much less than 1, theta into root over 1 minus m infinity square is much less than 1, and finally m infinity square into gamma plus 1 into theta by 1 minus m infinity square to the power 2 by 3 much less than 1. So, if all these conditions are satisfied, then the small perturbation theory is quite applicable. So, we have considered a subsonic flow past a wave shaped wall and obtained its solution, and we have also seen the validity of these conditions, and this results have shown us that a flow can be transonic for certain Mach number and body shape for a particular gas, but may not be transonic for another gas. That is, a flow transonic flow parameters or transonic condition depends on the particular gas itself along with the flow speed or flow Mach number and the body geometry. Also, we have seen that the parameters involved in this problem can be arranged in three groups or three parameters, where one is modified pressure and two are modified coordinates, and that modified pressure can be expressed in terms of the modified coordinates, and hence we can obtain a similarity rule for this type of problem, which gives a hint that for high speed flow problem perhaps it is possible to get similarity rules for many other situations, particularly when the problem is linearized or small within the framework of small disturbance theory. Also, we have seen that for a wave shaped wall, what would be the amplitude of the perturbation and what maximum thickness or maximum amplitude of the wall can be permitted, so that the flow can be treated as subsonic. In particular, we have seen that the perturbation has a attenuation factor in it, that is, the perturbation dies away as we go away from the wall. However, the attenuation decreases as Mach number increases, and so what we see that as the flow approaches incompressible, there will be no perturbation at all at infinity, which is the incompressible flow boundary conditions, that at infinity all the perturbation velocities are 0. However, that is applicable even for low subsonic flow, but as Mach number goes on increasing, the attenuation decreases. We have also seen that the perturbation is maximum on the wall and the pressure distribution on the wall is in phase with the wall itself. So, that the pressure on, considering a particular wavelength of the wall, the pressure on half of the wave balances the pressure on the other half of the wall. Consequently, there is no drag force acting in this case. So, we see that again in viscid two dimensional flow there is no drag force, which is true for incompressible flow as well. However, as we saw that in supersonic flow there is such drag, and we will next consider the solution of supersonic flow past this wavy wall, and we will see again that a drag force is present there. In other way, that the pressure will not be in phase with the wall, pressure will be anti-phase with the wall, and consequently a drag force will be present, which we found in earlier cases also, that in a supersonic flow there is drag even in inviscid flow, which is due to the wave nature of the supersonic flow. So, that we will be seeing here also. However, we will consider that solution of supersonic flow past this wavy wall in our next lecture.